Hello again. In this lecture, we will get an overview of what's inside a router and how a router works. This slide shows a schematic of a generic router. The packets enter the router through the input ports. The packets are next processed by the routing processor and the high-speed switching fabric. Finally, the packets exit the router via the router's output ports. Note that what we show as input ports and output ports are actually bidirectional. Each port can act as an ingress port or an egress port. To reiterate from the previous video, a router has two key functions, routing and forwarding. In this slide, we see that the routing function, which is in the control plane, is implemented in software. The forwarding function in modern routers, which is in the data plane, is executed in hardware and is implemented via the switching fabric. The forwarding function in modern routers, which is in the data plane, is executed in hardware and is implemented via the switching fabric. Note the time scale at which each function operates. The forwarding function operates at speeds 2 to 3 orders of magnitude faster than the routing function. The goal of any router is to complete processing of incoming packets at the rate at which they are received, which is termed the line speed. If the packets arrive faster than the forwarding rate, the packets must be queued for processing or they will be discarded. If we look at the input port in more detail, we see that the incoming message is received by the router at the line termination. Here, the bits that make up the message are detected and interpreted at the physical layer. The router's Layer 2 program then examines and strips the data link header and passes it to the network layer. The network layer process looks up the destination in the forwarding table based upon the IP header field values and forwards the packet to the output port. In the processing, the packet goes into an input buffer and is queued for forwarding by the switching fabric. The switching fabric transfers the packet from the input buffer to the appropriate output port buffer. Traditional forwarding is based strictly upon the destination IP address. However, note that forwarding can be based on other values in the IP header. The packet forwarding table will look somewhat like this diagram in this next slide. Note that the destination addresses are listed here in binary notation. If we look at the first row, all packets with destination addresses within this row are forwarded to link interface 0. Similarly, packets with destination addresses in the ranges shown in the next two rows are routed to interfaces 1 and 2 respectively. Any packet with a destination address falling outside these first three ranges is forwarded to link interface 3. This is also known as the default route. There will be some cases when the address ranges do not incorporate the same number of possible hosts, so there will appear to be some overlap. So how does a router make this decision? The router will look for the most specific route. It does this by finding the longest matching prefix. We can see this on the slide. In the forwarding table, the depiction of the address range has been modified so that the bits common to both the high and low end of the ranges remain the same. But where they differ, they are replaced by asterisks. You may recognize the asterisk as a wildcard symbol. In the first and third rows of this forwarding table, the last 11 bits of the 32-bit destination addresses are depicted with asterisks. In the second row of the table, only the last 8 bits of the destination addresses are depicted with asterisks. Looking at the first example at the bottom of the slide, the packet's destination address matches the first 21 bits of the address range of the first row of the forwarding table. So, this packet will be forwarded to link interface 0. For the second example, there are multiple matches. The packet's destination address matches the first 21 bits of the address range of both the second and third rows of the forwarding table. This ambiguity is resolved by the fact that the destination address matches the first 24 bits of the destination address range in the second row. Thus, the packet will be forwarded to link interface 1. As stated before, this is called longest prefix matching. To speed up this process, the longest prefix matching is often performed in TCAM, ternary content addressable memory. The word ternary in TCAM refers to the number of values that the memory can store and query. 0, 1, and a wildcard, the asterisk in our slides. CAM is a specialized type of high-speed memory that searches the entire contents in a single clock cycle. Data stored on CAM can be accessed by performing a query for its content itself. Due to its parallel nature, CAM, and by extension TCAM, is much faster than RAM. The switching fabric in a router transfers the packet from the input buffer to the output buffer. The switching fabric technology has evolved to process the ever-increasing internet traffic. The three basic types of switching fabric are memory, bus, and crossbar. The first generation routers use simple switching via memory. All the ports are connected to the same bus. 2 bus crossings are required to copy the packet into memory and then retrieve it from the same memory, thus limiting the switching speed. In the next generation of routers, each port has its own memory and packets are moved on a shared bus. The port operations are faster, but the switching speed is still limited by the bus bandwidth. Still, with large enough bus bandwidth, routers with this hardware are robust enough to handle the routing required for access and enterprise routers. The fastest routers use crossbar technology for fabric switching. A crossbar switch is an assembly of individual switches between a set of inputs and a set of outputs. The switches are arranged in a matrix. Packets from different input ports can simultaneously transfer packets to separate output ports. In advanced routers, packets are split into fixed length cells for faster processing. Of course, these fragments must be put back together. When packets arrive at a router, they have to be processed and subsequently set out. If the packets arrive faster than the router can process them, the router puts them into the input port queues, also called the buffers, until the router CPU can forward the data to the appropriate interface. If packets are coming in constantly at the line speed and the forwarding is slower than the line speed, the queues are going to build up and the amount of delay a packet experiences increases. And if the queue fills up, packets are going to be lost due to input buffer overflow. In the diagram, we see the condition called head-of-line blocking. Packets from 2 input queues, the red ones, need to be switched to the same output port at the same time. One of these will be blocked at least momentarily. This contention can then block a subsequent packet, the green one in the diagram. Output queues store packets until the router can serialize the data onto the physical wire. Packets can be dropped if the queues are not large enough to overcome traffic congestion. Congestion typically occurs when packets arrive from the switching fabric faster than packets can be sent out from the router. Scheduling policies are used to decide how packets are going to be queued and how they're going to be served. If the queues are not big enough, packets can be dropped. If the queues are too large, the packets can be delayed too much. Calculating the optimum size of the buffers for the queues involves trade-offs. Small buffers reduce queue delays and help maintain utilization of the network capacity, but they also increase packet loss. Large buffers have the opposite effect, but can increase the cost of routers dramatically. The rule of thumb in the past for buffering was round-trip time times link capacity C. This was based upon the desire to maximize link utilization and the behavior of TCP congestion control for a single long-lived TCP flow. We examined the TCP congestion control in our discussion of the transport layer in Chapter 3. Subsequent investigations have revealed that a very large number of TCP flows changes the cumulative behavior of TCP into a normal distribution. Thus, the buffer size recommendation has been reduced by dividing the original rule of thumb by the square root of the number of flows. This has dramatically reduced the costs of very large routers. Scheduling policies for packet switching are implemented in scheduling algorithms. Some of the algorithms are based on traffic flows or classes. Traffic flows are identified with a hash value generated from the following header fields: source and destination IP address, source and destination TCP or UDP port, IP protocol number, and differentiated services field value. The default form of queuing on nearly all interfaces is first in, first out, or FIFO, much like the queue to buy a ticket at a movie theater. This is also called first come, first served. If the FIFO queue becomes saturated, a configured policy tells the router how to handle the new incoming packets. Some choices are dropping the next arriving packet, or dropping the lowest priority packets, or even randomly dropping packets. Priority queuing employs multiple separate queues, each containing traffic with a defined priority level. Arriving traffic is classified with a priority based on certain criteria and is assigned to its proper queue. The airline boarding process is an example of this, with first-class and frequent customers boarding before economy passengers. Packets from a higher priority queue are always scheduled for processing before packets from a lower priority queue. Traffic within a queue is processed using FIFO. A major disadvantage of priority queuing is that lower priority queues can often receive no service at all, which is called starvation. Round robin is another scheduling algorithm that uses a separate queue for every traffic flow. Every active data flow is serviced in a periodically repeated order. If one flow is out of packets, the next traffic flow will take its place. Hence, the scheduling tries to prevent leaked resources from going unused. Round robin works well if all packets are the same size, but may not be desirable if the packet size varies widely. What might be a real-world example of this scheduling technique? Tier 1 help technicians may answer support calls on multiple phone lines using the round-robin method. The final scheduling policy we will look at is weighted fair queuing. Instead of giving each traffic class an equal share of the bandwidth, each class is assigned a different percentage. An example might be to give real-time traffic such as voice and video 60%, web traffic 30%, and all other traffic 10%. If all three queues are active, each gets the listed percentage. If the 60% wait queue is idle, then the other queues get 25% and 75% respectively, preserving the 1:3 ratio of their allocations. If the 10% queue is idle, then the other queues get 33% and 67%. This ends our basic discussion on what's inside a router and how it does its job. Next up, we'll talk about the IP packet.